My name is Christian Deterich, and welcome to Reverse Osmosis, a presentation on a promising global solution for an increasing water demand. And the problem we have here is that many communities and nations across the globe lack access to clean, freshwater sources for domestic use. These can often be countries along the coast with simply just access to the sea and nothing else. For developing nations, this can be devastating to health and the economy. And while this is going on, water use continues to grow at double the rate as the population is increasing. And furthermore, energy consumption is also an issue because the transporting of fresh water consumes a lot of energy. Furthermore, the conversion and purification of water consumes even more, up to 10 times as more as transport. The bottom line here is that the world needs an inexpensive and low power consuming method to have clean drinking and irrigation water. But how? This can be done through reverse osmosis, a membrane application. Here, reverse osmosis is a method of purifying water by removing almost all contaminants. And in this situation, we are taking seawater, which has too much salt to be drank, and converting it into potable water. This can be seen through the figure as pressure is being applied and water is permeating through the semi-permeable membrane, leaving behind all contaminants and having pure water at the bottom. The working principle for this is that the presence of solutes in water creates a natural osmotic pressure. And by applying a pressure gradient greater than that of the osmotic pressure, water will permeate through the membrane and salt will not. This is done by solution diffusion transport. And as seen here, at the molecular level, water passes through the membrane by dissolving through and transporting across it, rather than like in pore flow, where molecules are separated simply by size and fitting through pores. And for this, material selection must be taken into high consideration, and some of the requirements here is that the membrane material must have a high selectivity of water and high rejection of salt, and this will just result in the maximum efficiency and production of potable water. Material must also be able to support a high flux of water through the membrane, and to do this it must have a high mechanical strength. This is due to the extremely low thickness of the membrane, so that when these pressures are applied, it must be able to stay intact and result in a high flux of water for fast and efficient transport. And lastly, the material must be chemically inert so that it does not react with anything in the solution, which will result in fouling of the membrane, which reduces efficiency and flux. And one of the first materials ever used for the reverse osmosis membrane was made of cellulose acetate. It was effective due to its relatively high flux with respect to its thinness. And next, one of the most popular versions for reverse osmosis membranes today is the use of the material composite polyamide, and here it excels in quite a few ways over that of cellulose acetate, with the only drawback being chlorine tolerance. The polyamide membrane surface is shown here. As one can see, it is very rigid at the molecular level, which results in a high surface area and more room for water to efficiently transport across the membrane. The differences between cellulose acetate and polyamide can be seen here in these tables, and for cellulose acetate, the salt rejection can go up to 95%, while in polyamide it is up to 98%. This is good because some sources of seawater have higher salt than others, and some will require this higher rejection to be able to produce potable water. And next, the pH range of polyamide is much wider than that of cellulose acetate, with it being able to withstand 2 to 12, while the cellulose acetate can only withstand 4 to 6. This helps as the varying water treatments that are done before processing through the reverse osmosis membrane will be able to withstand the polyamide more so than the cellulose acetate. Polyamide membranes can also tolerate a higher temperature of up to 45 degrees Celsius as opposed to 35 in that of cellulose acetate. And for membrane configuration, one of the basics here is that it must be in a cross flow pattern, and what this means is that feed water is ran parallel to the membrane. This helps to reduce fouling and buildup on the membrane due to the velocity of the fluid passing by and it not allowing anything to attach to the membrane. Next is that reverse osmosis membranes are configured in a spiral wound membrane, and what this means is that they are done in a cylindrical way so that the water will permeate through the membrane and into the inner channel, while the salt will not and will be rejected out. Spiral wound membranes uses cross flow already and has a high surface area to volume ratio. The mass balance of these operations can be seen here through the simple reverse osmosis membrane unit, in which the feed consists of just water and salt, with the natural seawater composition of 96.5% by weight of water and 3.5% that of salt. And here you can see the permeate coming out the right with a high content of pure water and the retentate of a higher salt. And the mass balance calculations can be seen here through the percent recovery equation, and in most reverse osmosis membranes the standard of 75% is achieved through the polyamide membrane, which also has a natural salt rejection of 98%. And these equations were used in that with the mass balance to calculate the composition of the retentate and the permeate as well as their flow rates. The operating principles can vary and the parameters have implications on one another. This can be demonstrated through analyzing the effects of feed concentration, pressure, and temperature. Here the effective feed salt concentration is seen, and it shows that salt rejection decreases as feed concentration increases due to a higher presence of salt per mass, which results in more passing through the membrane. And for permeate flux, it decreases also with an increase in feed concentration due to how there is more salt passing through, which means less water will be able to transport. Here the effective temperature is seen, and as temperature increases, permeate flux does as well, due to a decrease in water viscosity, so they can move more easily across the membrane. Salt rejection also decreases as temperature increases, due to the transport coefficient of salt increasing, resulting in more passing across the membrane. Here the effective pressure is seen, with water flux increasing directly with pressure, which can be seen through the driving force, which is the pressure overcoming that of the osmotic pressure, showing a higher water flux. And salt rejection decreases as pressure increases, because the effective pressure on the salt is negligible while there is more water permeating. And in conclusion, as the water shortages around the world continue to grow, simple and inexpensive water purification technologies will become very valuable. And what this means is that hopefully through the further development of these membranes, the issue can be resolved completely and hopefully soon. Thank you.